In this illustration, we intend to simulate crushing of the S-shaped square tube in the Abaqus software. The tube is made of milled steel. The cross-section of the tube is square-like, and the general shape of the tube is in form of S. Here, a compressive load is applied to the top of the tube, causing that to be deformed. In this picture, the results obtained from the Abaqus software have been compared with experimental results. In this picture, the diagram of force displacement has been drawn, and as it can be observed, the results obtained from the Abaqus software are very close to those gained from the article. Actually, we intend to simulate this article in the Abaqus software. The article is entitled Experimental and Numerical Investigation into the Quasi-static Crushing Behavior of the S-shaped square tubes. As explained in the article, this test has been carried out for 6 samples having names of A1, A2, A3, B1, B2, and B3. In this educational video, we are going to simulate B1 sample in the Abaqus software, and here in this table, the parameters of tube have been distinguished. Actually, you need these parameters in order to draw geometric shape of the tube. Here in this picture, these parameters have been marked out. The length of tube is 1 meter and its thickness is equal to 2 millimeters. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create geometric shape of tube. I will select the modeling space as 3-dimensional, then deformable. From here, select Shell and Sweep. Enter approximate size equal to 5 and continue. First, I click on Create Construction and draw a horizontal line and a vertical line in this manner. Then I'll fix these 2 lines. In the next step, I will draw a slanting line. Enter the angle between this line and the horizontal line equal to 20 degrees. Then draw a horizontal line in this manner. I will enter the distance between this point and vertical axis equal to 0.5 meters. Enter the distance between this point and the horizontal axis equal to 0.075 meters. In the next step, I'll click on Create Fillet. Enter the radius of fillet equal to 0.95 meters, and then select these two lines. In the next step, I'll click on rotate, then on copy, select these lines. Done. Select this point as the center of rotation and enter the angle of rotation equal to 180 degrees. As you observe, the length of tube is equal to 1 meter, and in the article, the length of tube has also been considered to be equal to 1 meter. The distance between these 2 points is equal to 0.15 meters. I will click on Done. Then I should draw the cross section of the tube that is square-like. As it can be observed, the length and width of the square is 0.05 meters. I will click on Done. As you observe here, the cross-section of the tube is square-like, and the general shape of tube is in form of S. In the next step, I'll click on Create Part. I intend to create geometric shape of rigid wall. Here, I'll select Discrete Rigid, then Shell and Planar, and Continue. I will draw a square and enter the length and width equal to 0.1 meters. And done. In the next step, I will click on Tools menu, select Reference Point, and consider this point as the reference point of rigid wall. In the next step, I'll enter Assembly module. First, I'll enter Tube into the Assembly section. In the next step, I'll enter Geometric shape of rigid wall into the Assembly section. Click on Rotate Instance, select Rigid Wall, Done, and rotate that 90 degrees about Y-axis. In the next step, I'll transfer rigid wall to a proper place. I'll enter Property module, click on Create Material. As explained in the article, the tube is made of milled steel. I'll click on General menu, then on Density. The density of steel is equal to 7,800 kilograms per cubic meter. Then I'll click on Mechanical menu, select Elasticity and Elastic. Young modulus is equal to 210 multiplied by 10 to the power of 9 Pascal, and the Poisson ratio is equal to 0.3. In the next step, I will click on Mechanical menu, select Plasticity and Plastic. In this picture, you can observe the steel stress-strain curve. The yield stress is equal to 210 megapascal. OK. I will click on Create Section, select Shell and Homogeneous, and continue. The thickness of tube is equal to 2 millimeters. I'll click on Assign Section, select the tube, done, and OK. I'll enter Step module, click on Create Step. As explained in the article, dynamic explicit has been used in this question. I will enter time period equal to 6 seconds and OK. Here I'll enter the number of outputs equal to 120. Enter Interaction module, click on Create Interaction, select General Contact, continue. Here I'll click on Create Interaction Property, select Contact, and continue. I will enter the coefficient of friction equal to 0.3 and OK and OK. Then I'll click on Create Constraint, select Tie and continue. I will click on Surface, select the left rigid wall and done. Here I should select the surface that is connected to the tube. Here select Brown, click on Node region, and then select these lines. Done and OK. Again, I click on Create Constraint, select Tie and continue. In the next step, I will enter Load module. Click on Create Boundary Condition, select Symmetry, Antisymmetry, and continue. I will select the reference point of the right rigid wall, done, and close all boundary conditions of displacement for it. I will click on Create Boundary Condition. Again, select Displacement, Rotation, and continue. I will select the reference point of the left rigid wall, done. Here, I will close all boundary conditions of displacement except U1. I'll click on Create Boundary Condition, select Velocity, Angular Velocity, and continue. I will select the reference point of rigid wall, done. Here, I'll enter the velocity directed at x-axis equal to 0.025 meters per second. Click on Create Amplitude. Here, select Smooth Step and continue. Actually, as you observe in the article, in order to have the quasi-static condition established, we should use smooth step. I will enter Mesh module. Click on Assign Mesh Control. Select the whole tube. Done. Here, select Structure and Quad and OK. I will click on Seed Part and enter approximate global size equal to 0.01 meters. Then click on Mesh Part and Yes. Then I will click on Assign Element Type, select the whole tube. Done. Put the element library on Explicit and OK. In the next step, I will enter Job module and click on Create Job. The analysis was done successfully, so I'll click on Result. Here you observe the formation of the tube. As you observe, the results gained from the Abaqus software are so similar and close to those results obtained from the article, indicating that the question has been simulated correctly in the Abaqus software. In the next step, we intend to draw the force displacement diagram. Actually, we intend to draw this diagram in the Abaqus software. I'll click on Create XY Data, select ODB, Field Output, and continue. Here I'll select RF1 and U1, then select this reference point and click on Save. In the next step, I'll click on Create XY Data, then select Operate on XY Data and Continue. Here I'll select Combine. First, I'll select U1 and then RF1 and click on Save As. Here you observe the force displacement diagram. I'll transfer this diagram to Excel software. The first column is displacement, the unit of which is meter. The second column is force, the unit of which is Newton. Here, the diagram having been drawn with red color is the one obtained from the Abaqus software. As you observe, the results obtained from the Abaqus software are very close to those results gained from the article, and this indicates that the question has been done properly and correctly in the Abaqus software.